Hi, I'm Amit Paz from the University of Vienna. And today I'll tell you about our work with colleagues from the university and from IST Austria. This is about input dynamic distributed graph algorithms for congested networks. So this is a work in the domain of networks, and specifically dynamic networks that change over time. And we look at a fundamental way on this changing networks and how can we solve problems on them. So why are we interested in this, and what kind of networks and problems we're interested in? So we think of network control. We have a network composed of routers, computers, servers, and so on. And you want to coordinate traffic on it, for example. But the problem is this network changes over time in some ways. So for example, it could be that you have traffic patterns that evolve over time, over the day, or over the week. We can actually measure this, like the demand to transfer information from one place to the other, say in the internet. It could be a change to the network because the network operation from link weight updates for dynamic traffic engineering. So you have to recompute routing paths or find shortest routing paths. It could be the network operation update spanning trees, and we have to, in local area networks, we have to adjust to this. Or maybe content distributed providers modify cache assignments, and we have to adjust our network accordingly. And so the kind of questions you ask is these kind of problems. More theoretical perspective will say spanning trees, resource allocation, routing problems. Now you can think, for example, on software-defined network, wherein you can handle all these changes, but in a centralized way, or at least logically centralized. So you have to aggregate all the information about the system, the network, and all the changes into one logical unit, which is very heavy in terms of communication. On the other hand, you can think of distributed algorithms for solving these problems, but these may be very slow if you have to recompute everything from scratch anytime you have changes. So instead, we want to find something that have both advantages of SDN, or logically centralized control of a network, and distributed computing or distributed algorithms, where you don't have to aggregate all the information into one place. Specifically, the examples I gave, and for good reason, are examples where you have static topology and changing inputs. And the reason is that this is what we look at this paper. If we think of a network where the topology, the structure is static, there is a physical network, and the infrastructure, the physical infrastructure, is more or less stable. It doesn't change a lot. So you can count on this one not to change, but there are inputs, let's say edge weights or lengths or costs for using the edge, or maybe some subgraphing code. I'll talk about this in a second. So these inputs change over time, and you have to adjust to these inputs. And we are interested in distributed algorithms, control plane algorithms that solve these problems and do it fast without causing too much communication. So as a warm-up, think of a basic problem of minimum weight spanning tree, MST. We have a network represented here with the nodes for the units and edges for the communication links. And so we assume we have n nodes and computational units, and they're communicating through links that can transmit at most log n bits of a message in a communication round. So what do I mean? We split the time into rounds. We assume that communication is more or less synchronous. In each communication round, each unit can send messages to all its neighbors, but not too large. You can send one IP address or something like that, or your name, your ID, in a more abstract way to say IP address. But you cannot send the list of all the IDs of all your neighbors. This will take too long. You cannot fit this into one communication round. You can do it, but it will take more time. And what we try to minimize, our complexity measure here, is the time, the number of communication rounds. So this is because we assume that the local computation is very fast compared to the communication time. Now we take a distributed computing or distributed approach. So assume each node knows only about its local state, its name, say, its edges or communication links, maybe their cost or the rates, and that's it. No one sees all the graph. No one has a map of all the communication network. Sorry. And our problem in this example to build a MST, minimum weight spanning tree, under some edge costs. So our goal is to output this MST and even more. If you want to build a minimum spanning tree under this model, this is called the congested model of distributed computing. It will take square root n plus diameter time. We have upper and lower bounds for this. But what we are interested in today is not the computation, but the adjustment to changes. Let's say we have an algorithm that we used. We build a minimum spanning tree. Now there are some changes to the edge weights, to the costs. Some become heavier, some lighter, some more expensive, some cheaper. There are alpha changes. We use the parameter alpha to denote the number of changes. And now we want to update the minimum spanning tree. We could, of course, recompute from scratch. It will take square root n, but what if alpha is very small? There are just only a few changes. Can we do better? And we try to do a systematic and formal study of this. These questions were studied before in networks, of course. And another approach is dynamic graph algorithms. They're also very well studied. They also give a systematic and formal study of these kind of problems. But in dynamic graph algorithms, we assume a centralized entity that controls the network. Here it's all distributed. So most of the results on dynamic graph algorithms do not apply here. So we have to understand the limits and the abilities of distributed dynamic algorithms for networks. So how do we handle this minimum weight spanning tree in less than square root n time? Well, we can do it faster in alpha time, alpha plus diameter. We assume that we only want to handle changes that come after some time. So before the changes, the network has a lot of time. Each node will aggregate and store all the old weights and all the topology of the graph before the changes. Now, when there are alpha changes, we broadcast them to all the nodes. So each node knows only about its own changes, but it can broadcast it to everybody else, either by flooding, sending everything to everybody, or by building a BFS tree, breadth first search tree, collecting all the information on this tree, and then propagating it to all the units. And now each unit knows all topology, all weights, and also the changes. So it can compute the new structure of the graph, the new weights, and accordingly a new MST, new minimum spanning tree, and then output which of its own edges is in the MST. And we can show that this takes time alpha plus diameter. Diameter is the longest distance between a pair of units in the network. And basically this is because the broadcast of the changes will cost this. And if you want to broadcast all the changes to everybody, you cannot do fast. But can you do faster in a different way? Can we have a faster algorithm for MST under alpha changes? Well, good question. But to answer this, let's talk a bit more from a fundamental approach on these kind of questions and the model and so on. So the type of problems we look at in this work are two. One is subgraph problems. There is the network, the static network, it doesn't change, and the input represents some subgraph, some edges that exist or don't exist in the subgraph. And in this subgraph, you want to solve a problem, say finding small network motifs, small structures like triangles, or one extension of triangles is cycles of some length, given length. Another extension of triangles is cliques, a set of nodes that are all connected to one another in this input subgraph. Another type of questions is weighted problems, where the input of the edge is not if it exists or not in the subgraph, but what its weight or cost. And then you, of course, ask about MST, minimum spanning tree, as I mentioned before. Maybe diameter, weighted diameter, like the longest distance between a pair of nodes, when you take into account the weights of the edges, the cost of them. Or maybe shortest path between all pairs of units, or finding the paths, finding just the distances. So these are the type of problems we look at. And the algorithms we build have the following structure. There is an answer, say minimum spanning tree. There are some alpha changes, and now the algorithm runs on the old graph with the changes and produce new output, new minimum spanning tree. And then we go back to the beginning and have to, again, get more changes and handle them as well. So under this model, which we call the batch dynamic congest model, what is the complexity of different problems? It could be a function of alpha, the number of changes, function of d, the diameter of the graph, maybe function of n, the number of nodes in the graph, or m, the number of edges even. But actually what we see in this work, that alpha is the main parameter, the number of changes in a batch, and different problems have very different complexities. First of all, note in the end of the slide that there are no complexities above alpha plus diameter. We thought there could be problems that even if you have alpha small, few changes, you need n, the number of nodes or something like that, but no. Alpha plus diameter, in alpha plus diameter time, you can solve any problem basically by the algorithm I showed at the beginning. And this includes problems like minimum spanning tree, diameter, all pairs of spots, APSP, distance between all pairs of nodes. And for this problem, we know that this is more or less tight up to polylogarithmic factors. Other problems, like k cycles and 4 cycles, we have different complexities. We know that we can solve them in alpha time. We don't need to pay diameter. And then we have lower bounds for 4 cycle. The lower bound is alpha to the 2/3. And for k cycles, it's square root alpha. So you cannot expect to find k cycle for constant k at least 5 in less than square root alpha time. Another question we look at is k clicks, a click on k nodes that are all connected to one another in the input subgraph. And this has complexity between alpha to the 1/4 to square root alpha. So it cannot be that all problems are either super fast, super easy and can be solved in constant time, or all take at least alpha time. Some, like k-click, have polynomial time that is not trivial, not in the 2 endpoints. So how do we solve this k-click, the click detection problem? So what is the problem? There is some input or some known value parameter k that's known to everybody. There is a graph encoded by labels of 0 and 1. They're inside the big graph, which of the edges belong to the graph or not. And now in this subgraph, you want to answer yes. Each node will have to answer yes if it's a part of a k-click, and no if it's not a part of a k-click. And this makes sense actually to look at this input, the local input. If you want everybody to know if there is a click or not, you have to pay another diameter time to send to everybody if you find a click. But here we want something very local. Each node by itself has to know if it's part of a click of size k or not. And that's all we care about, not in global knowledge. If you think of this problem in a non-dynamic setting, say in a model where the messages are unlimited in size, then this problem is very easy. Just tell everybody about all your neighbors, and in one communication round, everybody know if they are part of a click or not, if each of them is a part of a click or not. If you are in the congest model I mentioned in the beginning, this will take square root n rounds. We know this, actually. We have a lower bound for this. But what I mean if in the model we care about today, the batch dynamic congest model, where there are changes. So a trivial algorithm like the one I showed at the beginning, more or less, will take alpha time. Each node will tell all the nodes, not about its neighbors, but about its changes, the changes it belongs to. But we show you can actually do much faster and get square root L in an alpha. And with the polynomial lower bound of alpha to the 1/4, it means that this problem has an intermediate complexity, as I just mentioned before. So how do we do this square root alpha time algorithm? The idea is to use the key ingredient, at least, is the bounded out degree orientations. So we say that the graph G is d-degenerate if it has orientation with out degree at most d. In this figure, you can see a graph with, that is 1-degenerate. You can orient all the edges like a tree, where each node has only one outgoing edge. And now we can also prove that if you look at the subgraph composed only of the changed edges, so it's a subgraph of a subgraph actually, only the edges that change, if most alpha edges changed, you can orient the edges of it such that the outer grid is at most square root alpha. And now we assume that each node can get ready for the changes. So we'll store the labels and the edges between all its neighbors. And when there are changes, first we compute in a distributed manner this square root alpha outer grid orientation of the edges that changed. And there are actually fast distributed algorithms for this that take only log square alpha time. And then each node will broadcast the labels that changed, but only of the outgoing edges of it. And it has at most square root alpha outgoing edges, but this is enough. So in total, in square root alpha time, we can find all the clicks because each node knows about the edges that didn't change and got messages about the edges that did change. How do you prove that we need at least alpha to the 1 over 4, that you don't have a super fast algorithm that takes constant time? So we start from the non-dynamic congest model, the congest model I mentioned at the beginning, where there's just a network and you want to solve a problem. Say you want to find clicks in a network, a static network, doesn't change. So to prove this kind of lower bounds, we use reduction to communication complexity. Communication complexity is a well-studied topic in theoretical computer science, where you usually look at two players, call them Alice and Bob, and they want to compute some function on their inputs. Alice has an input x, Bob has y, and let's say they want to know if x equals y, or x is a set, y is a set, and they want to know if their sets are disjoint or do they intersect. This is a function of their two inputs, and they have to communicate something about their inputs to solve it together. So what we do when we have a problem on graph, a distributed problem on, say, the congest model, we assume there is an algorithm for this problem that runs in time t. Now we build a specific instance, specific graph family that depends on the problem and on the inputs of Alice and Bob. And now Alice and Bob, in order to solve their problem, say equality or disjointness, they simulate the algorithm on the graph. The algorithm finds clicks. And then you build the graph in a specific way, so such that, for example, if there is a click, then the sets are disjoint. If there is no click, the sets are not disjoint, or something of this flavor. If the Alice and Bob simulate this algorithm, they can solve their own problem. We have communication complexity lower bounds for these kind of problems, like F, disjointness, from which we get lower bounds back in the congest model. So this is a classical way to prove lower bounds for the congest model. We use something similar for the batch dynamic congest model that I mentioned. Here it's a bit more problematic because you cannot build a graph every time. You just can have changes that depend on the inputs. So we build a family of graphs that have more edges than you actually need. Some of the edges will be changed. Alpha of them will be changed. And then we do simulation, more or less like in the previous slide, in order to solve a two-party communication complexity problem. So this is just a high-level idea. And it works for many problems, not just for k-clicks. These are a table of all of our results. I will not go over it. I'll just mention one aspect that is in this table that I didn't talk about at all, which is the memory. How much memory, how much space you need to use on each node by itself. For example, for minimum spanning tree, the algorithm I showed at the beginning will take alpha plus diameter time and m times log n space, the algorithm I started from. You have to keep all the graph. So in terms of time, this is actually more or less tight. But in terms of space, we can do much, much better. We can have just logarithmic number of bits in each node instead of keeping all the graph in each node. Our future plans and open questions is to study more upper and lower bounds for different problems, or for the problems we studied, find more refined bounds. Understand space better. Currently, we don't really have good techniques for proving space lower bounds. And looking at other problems and other models like the local model. What happens if the messages are unbounded in size? We still have interesting problems that we don't know how to solve with dynamicity. And I will stop here. Thank you very much.